This video is going to talk about the distribution of the sample variance and some related distributions. So the first thing we need to do is we need to make sure we understand what we mean when we talk about the sample variance. So the sample variance, S squared, is how we denote it, is 1 over n minus 1 times the sum, I equal 1 to n, of xi minus x bar squared. So this is in the situation where we're taking a sample size of size n from some sort of a distribution, and we are taking that random sample and then trying to measure variability within that sample. This would be used to try to estimate the variance in the population that we're taking a sample from. And you've probably seen this measure in some introductory statistics classes before. So a theorem in section 5.5 tells us that if we have these n observations as a random sample of size n from a normal distribution in particular, then if we calculate this sample variance, then the sample mean and the sample variance are independent, and that the n minus 1 times the sample variance divided by the population variance has a chi-square distribution with n minus 1 degrees of freedom. And there is a proof of the second portion of this in the book. It's quite detailed and long, so feel free to read through. If you have questions about it that you'd like to ask, I'm happy to answer them. But in the meantime, we're going to just sort of take those and work with them. Now, also in section 5.5, there is a definition introduced of something called a T distribution. And what we're told is that if we have a random variable z that has a standard normal distribution, normal with a mean of 0 and a variance of 1, and we have another random variable u that has a chi-square distribution with r degrees of freedom, then if those are independent, then the random variable that we get, we'll call it t, which is that standard normal random variable divided by the standard deviation of our chi-square random variable divided by its degrees of freedom, has what we call a T distribution. So this isn't something we're proving, it's something we're defining. And it can be shown, although that we're not going to do so, that the distribution function, the PDF of this T distribution, has this form. Now, we're going to use that theorem and that definition together to learn about an important statistic that's used in inferential statistics. So, given a random sample, x1, x2, up through x sub n, from a normal distribution, we already know that the distribution of the sample mean, x bar, has a normal distribution with a mean of mu and a variance of sigma squared over n. By standardizing this, that means that z, the quantity z, which is the sample mean minus its population mean, divided by sigma over the square root of n, has a normal distribution with mean 0 and variance 1, so that's a z distribution. We also have a theorem that stated that if I take n minus 1 times the sample variance and divide it by the population variance, that I get something that has a chi-square distribution with n minus 1 degrees of freedom. So now if I want to, using the definition of the T distribution, I have something that has a standard normal distribution. I'm going to divide it by, just to refresh our memories here,
something that has a chi-square distribution with r degrees of freedom. So I'm taking the square root. Now I know that this u here, n minus 1 times s squared over sigma squared, divided by its degrees of freedom, and it has n minus 1 degrees of freedom, is going to have a t distribution. And it's going to have a t distribution with n minus 1 degrees of freedom. Doing a little algebra here, I can simplify this. This gives me x bar minus the mean over sigma over the square root of n divided by s over sigma, which gives me x bar minus the population mean divided by s over the square root of n. And this is our t. So what that means is that this quantity here has a t distribution, as long as I'm sampling from a normal population. And the degrees of freedom, again, are equal to n minus 1. Now, this is a very important result. It's the reason why we use a t distribution in our sort of introductory and even beyond that. Anytime we're making hypothesis tests or making confidence intervals about a mean, we always work with a t distribution. And the reason that we have to do that is because if we are trying to understand a population based on sample data, and I don't know what the true population mean is, I'm also not going to know what the true population standard deviation is. And so instead of being able to throw in our sort of sigma into our formulas, we're going to have to use our sample standard deviation. So it's very important to understand the distribution of this quantity. And I'm going to just do a quick example to illustrate how this could be used in inference, and then we'll leave it there. So a claim is made that the distribution of heights among all adult men in the U.S. is normal with a mean of 71 inches. A random sample of 20 adult men living in the U.S. is selected. The average height among the men in the sample is 69 inches with a standard deviation of 3 inches. Is this strong evidence to suggest that the mean height of men in the United States is really less than 71 inches? Okay, so again, we're going to approach this by deciding, okay, if the mean height really is 71 inches, what's the chance that we'd see a sample with a mean as low as 69 inches? Right? If the sample data is something that would be very unlikely to occur if the true mean height were 71 inches, then we say, well, probably the mean height is not 71 inches. Right? So that's what we're going to be looking at. So if the mean is 71 inches, that would mean that the quantity x bar minus the mean over s over the square root of n has an approximate t distribution with n minus 1 degrees of freedom. And this would be true because we're thinking we're sampling from a normal distribution. We don't know what the population standard deviation is, but we're given the sample standard deviation, so we're going to need to be using that. And so in this situation, say, okay, well, the probability that the sample mean would be less than or equal to 69 inches is the probability that the sample mean minus 71 over S over the square root of n is less than or equal to 69 minus 71 divided by S, which is our sample standard deviation, is 3 inches, and our sample size was 20. We know that this quantity, if the claim is true, has a t distribution. So that's the probability that we'd have a t random variable with n minus 1 degrees of freedom have a value less than or equal to, doing this math, negative 2.9814. And again, I can use either technology or I can use a table to find this area in a t distribution. So what I'm be looking for is to say, okay, so I've got a t distribution. T distributions are centered around 0. And I'd be looking to see, okay, what's the area down below negative 2.9814 in a t distribution with 20 minus 1 equals 19 degrees of freedom. So just to work through that, because we haven't used a t distribution on the calculator yet in this course, if you're working with a TI-84, the way that I'd find that is I'd use the t-CDF function. I'm going to put in the lower limit, which is going to be my negative infinity value. Since I don't have an infinity button, I'm going to put in negative 10,000. I need to put in the upper limit of this area, which is going to be negative 2.9814. And then I need to put in my degrees of freedom. Degrees of freedom are 19. So as I come in and do this, come to my distributions, I've got the t-CDF. Again, I'm going to use a very small negative value. Negative 2.9814. My degrees of freedom are 19. And that gives me a probability of 0.0038, rounded to 4 decimal places. So if the true mean height in the population of all U.S. men is 71 inches tall, the chance that we'd get a sample, a random sample of 20 men in the United States that would have a sample mean of 69 inches or smaller is only 0.0038. So it would be very unlikely that we'd see a sample mean like this if really the true population mean is 71 inches tall. And since that is what we actually saw, there are kind of two possibilities. Either we saw something that was very, very unlikely, or this claim is not true. And so since this is such an unlikely result, I'm more inclined to believe that the claim is not true. So there is strong evidence to suggest that the mean height among all men in the U.S. is less than 71 inches. And again, this is really essentially how we do a hypothesis test for a hypothesis about a single mean. We'd do it using a t-distribution because we would not know the population variance, and we'd need to be estimating it with the sample variance. Anyway, I hope that these last couple of lessons have given you a little bit of insight in sort of some of the theory that underlies the methods that you've seen in other courses, often without a lot of discussion of the theory, and that you will ask me if you have any questions. Have a good day. Bye.